We have written a complex number z as x plus iy, where x is the real part and y is the imaginary part. There's another way to write a complex number, which is called the polar form. What we do is we put the complex number z in the xy plane in Cartesian coordinates. And the x-axis here we call the real part of z. And the y-axis here we call the imaginary part of z. So we position z as x plus iy, where the x-coordinate is x and the y-coordinate is y. We can draw a vector from the origin to the complex number. The vector then has length r, and the angle it makes with the x-axis is theta. So we can use trigonometry to compute x. So x, right? So x is adjacent over hypotenuse times hypotenuse. So it would be r times the cosine of the angle. And y is this vertical distance here. So y is opposite over hypotenuse times hypotenuse. So it would be r times the sine of the angle. So this is sometimes called polar coordinates. If we put it together to form z, then we have z equals x plus iy. We can factor out the r, so it becomes r times cosine theta from x plus I sine theta from y. And then this is our well-known Euler's formula. So this becomes r times e to the I theta. So z equals r e to the I theta is what we call the polar form of the complex number z. So let me write that up here. So x plus iy can also be written as r times e to the I theta. We have the formula x equals r cosine theta, y equals r sine theta. So you may ask, well, can we invert this and write a formula for r and theta? We can if we square x squared. If we square x and we square y and add them, we'll get r squared cosine squared theta plus r squared sine squared theta. But cosine squared theta plus sine squared theta equals 1 from the Pythagorean identity. So x squared plus y squared equals r squared. So that tells us that r is equal to the square root of x squared plus y squared. R is a length, so r is positive, so we just take the positive square root. On the other hand, to get theta, we can divide y by x. Then the r cancels, and we have a sine theta over cosine theta. So we end up with the tangent of theta is equal to y divided by x. And then to take the arctangent of this, you need to decide, know which quadrant z is in order to do the arctangent correctly. So that sometimes takes a lot of work, but here we'll just leave it as an expression for the tangent. Okay, this e to the I theta, because it's cosine theta plus I sine theta, is a periodic function. So we should realize that if k is an element of the integers, so integers we call capital, we call that blackboard z. So if k is an element of the integers, then e to the I of theta plus 2 pi k is equal to e to the I theta. So this theta angle isn't unique. You can spin it by 2 pi in any direction, clockwise or counterclockwise, and you end up with the same expression. So sometimes that's very important to remember that this theta angle is not unique. Finally, the polar form of a complex number makes multiplying two complex numbers very easy. So if we have, say, z1 equals r1 e to the I theta 1, and z2 equals r2 times e to the I theta 2, then the product of z1 and z2, z1 times z2, can be obtained just by multiplying the r's, so r1 times r2, and adding the thetas because of the way the exponential function works. So I theta 1 plus theta 2. And sometimes that will make arithmetic in problems such as differential that you obtain in like differential equations a lot easier. Another thing to note that if r2 was equal to 1, then multiplication by e to the I theta 2 will just spin this vector counterclockwise through an angle theta 2. Okay, let me summarize. So the polar form of a complex number is writing x plus iy as r times e to the I theta, and that we can invert for r and theta. So r is the square root of x squared plus y squared, and the tangent of theta is y over x. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.